actually achieved from smaller matrices or by aggregating, so list of lists is used. But then still using it for numerical linear algebra operations like matrix by vector product, we're discussing matrix by vector product here. The compressed sparse row, CSR, is the main one. For the transpose, you can do the column, and there are block elements, and SkyPy has the routines that allows you to go from one format to another. So coordinate format, you store 3 arrays, one integer array, another integer array, and all of these 3 arrays have the length that is equal to the number of non-zeros in the matrix. So this is what we store. So good, it's a very simple format, but it's not good for matrix by vector product. So it's not optimal for storage. We'll show you in a second. It's not optimal for matrix by vector product, and it's not optimal for removing elements. If you want to take an element out, so adding is simple to the coordinate format, you just write an n, but then I say I want to make this element 0. This is not good in the coordinate format, and the first 2 disadvantages, they are solved by this compressed sparse row format. Okay, you can use clicker to show it. So, but I still need to reduce the size. So, compressed, that's an important story, so let's be slow here. So the compressed sparse row CSR format, we use 3 arrays again. Well, historically, again from an old Fortran code, they're called ER, JA, SR. So this is the array of length n plus 1, where n is the number of rows in the matrix. GA, these are the column indices, which is the integer array of length n and z, and SA, it stores the values. Okay. So now we have saved one integer array compared to coordinate format, which is not a big reduction, but still, it's good to know that you can store the same data with a few number of bits. And this is the illustration. So I have not explained why compressed, I just explained by examples. This is our sparse matrix. And what we do first, we just put together all the non-zero values. And we go by row. 1, 5, 2, 3, 4, 1, 2. 1, 5, 2, 3, 4. So we go through each row and put all non-zero elements consecutively. So this is the array of values. We also save the column indices. So, for example, this one is located in the column with number 0. We put 0. This is located in the column with number 2. We put 2 here. And so on. This one is located in column number 0. So these are column indices. So that's exactly what we would have for the coordinate format. So these are the column indices. What we do not store the row indices. Why? Because when we take these 2 elements, they are located in the same row. And we don't have to store the same row index. We only store the information where a new row begins. So the first row begins here, the second row begins here, and so on. So this would be in the first row, this would be in the first row, this would be in the second row, this would be in the third row, and this would be in the fourth row. Okay? And we also put the array of length n plus 1 for convenience. So basically, I'm just saying it. So and why compressed rows? rows, we take each, if you have just a sparse vector, in order to store a sparse vector, we need to store the location of non-zeros and the values. And then we take the sparse vectors, compressed rows, put on top of each other, and just store where each row ends. Another way, we might just store the total number of non-zeros in each row. That would be enough to find out where are the non-zeros corresponding to a particular row. Okay? Any questions?
What do numbers in the rows start arrays mean? What is 7, for instance?
These are indices in this array. So it says the first row of the matrix starts at position 0 here. So we need to find out that these two elements were in the first row of the original matrix. How we do that? We say the first row starts here, and the second row, okay, 0th row starts here, second row starts here. So if you just, paint, right? So this would be 2 elements, 1, 5 would be 2 elements from the 0th row, 2, 3 would be 2 elements from the first row, and so on. So they point, formal definition, they point to the first element of the corresponding row. And these are pointers in these compressed arrays. Any other questions?
Yeah, it's very nice to store this kind of way, but as you can see that you need additional operation to restore the matrix and to do any kind of multiplication with a matrix by vector, or something there. So the question in my, how profitable is it in terms of performance?
Yeah, that's a good question, and we will discuss it in the next slides. So actually, for matrix by vector product, this is a good representation. So storage we compress, but actually that's not the main goal, because we only remove one integer array. One integer array, well, in terms of bytes, it's much smaller than the real array. The main goal is the reduction of complexity of matrix by vector product. So in PyTorch and TensorFlow, there is some support. So coordinate format is implemented, in some backward operations is implemented, but again, CSR, as far as I understand, not implemented, but for sure it's also difficult to do, actually. And if you can volunteer to implement it there, why not? And that's the main, how we multiply a matrix by vector and such format. So the data is stored in 3 arrays, I, G, A, S, A, and that's how the code looks like. So we need to compute the product. Compute the row by column, and we have a compressed row. So we just go through all the elements in the result, and the ith element of the result is just the scalar product of this compressed row by column. So you take the values of the compressed row, and then you take the values of the vector we are multiplying with at corresponding columns. That's all. So we use this, and then the range, it starts from the start of the row through the end of the row. So the number of non-zeros per each row is just the difference of this guy minus this guy. So if they coincide, this would be an empty cycle. So you do not do anything, well, you have to initialize y by zeros here. So that's how you use it for multiplication. And if you think a little bit how to implement the matrix by vector product in the coordinate format, it will be much more complicated. Well, not much, but yeah. So consider again the two-dimensional Laplacian case. Now we take a large example. So what we do, we make a coordinate matrix in the coordinate format and the CSR matrix, compressed sparse row format, and we compare just the tangles. How fast each of those are. But actually this is a good matrix because it is very regular. So it has so-called, well, the difference, well, it's like 30%. Not so much, but well, it's noticeable. But if you have a more unstructured sparsity patterns, not like diagonals, the difference will be larger. Okay? So this is the summary. So such kind of representative, they of course give complexity reduction in terms of floating points operations that is made. Because we just make fewer floating point operations if the matrix is sparse. We will discuss it in a second. They are not very good for anything else. So dense matrices, they are very good because the data is a square, and for example, matrix by matrix multiplication is a cube, so you have really utilized, you are really utilizing the CPU. You are really utilizing floating point units. You have, on each number you do much less number of reads and writes compared to the operations. If you count the number of floating point operations per second, you will get numbers that are close to the peak performance of a particular machine. That's why all these peak performances are typically reported for dense linear algebra, not for sparse linear algebra, for dense. Now you can see you have 80%, 90% of performance of a supercomputer. But again, it's maybe not efficient in terms of flops, but in terms of actual computation time, it may be much better. So a good peak efficiency, if you now count the number of floating operations you make, and you just floating point you make, and divide by the actual running time, or if you get 10 or 15%, this is a very good code. Yeah. So you can measure this, such kind of tests. And this test, I've said it somewhere in the beginning, but for any program, if you want to say that your program is fast or efficient, measuring flops is always a good idea. Because you can compute how many floating point operations your code has, compute the actual running time and divide them. And if you get bad numbers, that means that your code is not efficient, or you need to explain why it is not efficient. But this is a very good test. Maybe you get 100% efficiency already and you cannot optimize. So this is just matrix director product of a 4,000 times 4,000 matrix. So if you do that, the running time is 10 to minus 2, something like that. So 9 milliseconds. The efficiency is 4 gigaflops. It's actually not too much for this mark, for many reasons. We are not using parallel computations there. There is a lot of things running on top and so on. So even multi-core is not utilized. But still it's, well, 4 gigaflops. So let's do a sparse matrix by vector product. And just take a tridiagonal matrix. So we now take a 400 times 400 tridiagonal matrix. So the time, okay, let's take it 4,000 to compare. So for 4,000, the time there was 10 to minus 2 seconds. Here the time is 10 to minus 4 seconds. It's more than 100 times faster, but the efficiency is like 64 megaflops, which is very, very low. But the actual running time is slower. And this is a good and very regular matrix. Yeah, here I can do whatever, 4,000. So if you go larger, yeah, problem on the peak performance of this algorithm, right? So 0.5 gigaflops. So this is like 10% of what we had for 10, well, 1%, right? It's 1%. So there we had like 4 gigaflops. This is a huge matrix, 400,000. It's 1%. This is 1%. But still the time is... So this is all related to random memory access, which is happening in this computer and everywhere else. I'll just briefly explain the basic concepts and what can be done in principle if such kind of performance is crucial. So maybe this is a bottleneck. Maybe this is a matrix bidirectional product is a bottleneck. What can be done? But before I explain what can be done, let's understand what's happening. So all elements are stored in this in operative memory. So then the CPU actually wants to make some computation and it checks whether the data is in the cache or it's in the operative memory. So if it's in the memory,